in Vyper. Actually,
Yes.
how would everybody say their familiarity with it is with Solidity, Vyper, IR, assembly, EVM stuff?
I think
Just
would be nice for us
mention in
to,
the chat.
yeah, the assembly would be a common point. Bytecode would be a common point.
Cool. ST transformation is a weak spot for me.
Is that Vim?
This is Vim. I'm waiting for some other people to respond. By AST transformation, I assume we're kind of talking about what happened, the kind of code gen. Like, how do we go from AST to like something more level and then transform that? So, first of all, let's just like look at this because I actually don't know what's in here. In fun, decimals. Make this like immutable. This stuff hasn't been updated in a long time. This could also be immutable. Then basic Vyper, most unknown to me, readability wise is easy. Yeah, so let's just go through this. So first of all, the biggest difference between Vyper and Python is that Vyper is statically typed and somewhat strongly typed actually. So you can see here that everything here has a type annotation. So the first thing we're going to do is, hopefully I haven't made any mistakes. And we're going to first look at the unoptimized stuff. So let's look at the ASM and opcodes. And let's look at the so we've got all of this. Actually, let me remove the opcodes for now. So the first thing we see is all of these functions. So what are all of these? So we've got a bunch of things like so we've got a bunch of things like deload, destore, no destore, iload, istore. So these are interesting because these are happening in the constructor. So this istore is a special section that we have for immutables. But before I get into that, let's like look at the overall structure of this. So we've got the init function, and that does all this thing, all this stuff. And then here, this is all the init code. And then the last thing in the init code is to deploy the runtime code. And so here's the runtime code. So one big difference between Vyper and Solidity or Yule is actually that this IR is pretty low level. There's no object sections. That this is literally just like this is going to turn into to EVM code.
Is this Python assembly?
This is an intermediate representation. So it's not really assembly, but it's pretty close. So if we maybe I shouldn't have started with such a complicated example.
No. This is really interesting. This is really interesting. Please keep on. I just have one question. People keep on repeating intermediary representation. Can you actually explain for us what is that?
Yeah. So intermediate representation is what happens. It's the intermediate stage. So if we have like, let me make some really simple example actually. This is a good example. So if we look at what the AST is like, it's like not very interesting. It's just a tree representation of this whole thing. You just have like um we've got a bunch of AST nodes. It's like you look at this thing, you have an external token, you have a def, and then inside of that, it's like a tree, inside of that you have this statement, and this statement is composed of, like these five different things. And it's basically just describing what the source code is. Control C plus Control V says, is this Venomire? Yeah, we've renamed it to Venomire. This used to be called LLL, but we've started making so many changes to it. And in fact, planning some larger architectural changes, which I haven't gotten around to yet. So kind of renamed it Venom, and so the compiler for the intermediate representation is called Fang. Of course, there's something wrong with my installation directory.
It's okay. It's okay. Why do we need to have an intermediary representation?
Yeah, the reason you want to have that's a good question, and I was about to get to that. The reason you want to have an intermediate representation is because if you go directly to assembly, so oops, which is something like this, which is like basically bytecode, it's really hard to optimize. So let me show you some things that you can optimize in IR that are a bit harder to do in assembly. So here's actually
Makes a lot of sense,
runtime.
talking about optimization. Makes a lot of sense.
Yeah, let's just get the runtime for this. So oh, sorry, I thought this was a constructor. But anyway, that's fine. So here's the unoptimized version of this thing. So we have all of these things, like assert greater than or equal to assert call data size greater than or equal to 36. So one thing that is kind of a lot easier to do in the optimizer is like it's actually let me look at, oh yeah, cool. So here's one. So for example, here we see like if this thing is equal to that thing. And then it turns out that it's actually better to use an XOR with an is zero here, and that's because this gets compiled differently. So if we sorry, I'm gonna remove this other function for now because it's distracting. So if we look at what that looks like in the runtime, is we have like this weird branching thing, right?
Okay.
To eq is zero, and actually, since we were able to move some things around, this isn't even the best example.
No, no
Um,
problem, bro. Keep on.
yeah, so like we're able to move around items more easily. So if you look at these things, like we're trying to check, if this top, if the call data, if the thing that we got from call data load is like equal to this thing, and then if we were to do this on the ASM directly, or the opcodes directly, it would be a little bit more complicated because we have to like have a model of, in particular for the EVM is our backend. So in particular for this backend, because by the time we get to like EVM, we need to like have this idea of what the stack is like. We have to have a model of what the stack is like. And if you look here, there's no stack. Um, Everything is kind of like, we've got variables,
Nice.
so we can do things like reorder variables. We can reorder the order of in principle, we can reorder this and this.
One more question that I have for you is how do
Yeah,
you
sure.
code those optimizer detectors? So how did the optimizer came to the conclusion that was better to use a XOR with zero in there instead of doing the non-optimized way?
That's a good question. This is kind of, I mean, some
Oh, this is
somebody
so
had to come up
sexy,
with the
bro.
rule to begin with. Yeah. So, I mean, this is an optimization I came up with a while ago. It's inspired by the fact that in x86, it's actually the way you zero a register is actually not loading zero into the register, but you XOR with itself. So XOR has the property that if you XOR something, and XOR turns out to be faster on CPUs than than loading into a register. And so XOR has the property that XORing something with itself returns zero, and XORing something with anything else returns something non-zero. So um, there's some things here. So like commuter things you can move around, but yeah.
This is really cool.
So right.
Uh, one
um,
one question for you though. This is some inspiration you took from somewhere where the research to build this came from.
uh, in this particular rule or the framework as a whole.
Yeah, like the framework as a whole. I mean, building an optimizer, you gotta have some experience with, x86 and so on.
I think EVM experience is actually more important, although having
Nice, good input
a
actually.
general idea about yeah, I mean having general idea about like compiler lore for other things, which you can just find out by reading stuff online, is helpful. Um, and then I think optimizers are actually probably the most complicated part of any compiler because I read somewhere that like something like I, I don't know about this statistic, but 70%. Basically, most of stuff that needs to be optimized in a compiler is actually stuff that's generated by the compiler because you don't op because when you translate AST mechanically into bytecode, um, you kind of use a lot of abstractions, and then the abstractions end up costing, and then kind of you have to optimize to like get rid of the abstractions. Um,
How do you go
and
about testing
optimizations are
this
hard. How do we go about testing them? I mean, this particular rule or in general?
in general, like testing the optimizer itself?
Yeah, I mean, obviously, you have your front line. You have like some unit tests. You kind of like optimize a bunch of code and see if it breaks. Um, Generally, we're more conservative. We're pretty conservative in the optimizer. I think Solidity and anybody else generating code for EVM is too. Um, and then like a lot of thinking. So like anytime you make any change to any optimization, you have to think about it a lot. Um, and I think there really is no substitute for thinking. Because like a lot of you know, the optimizations are not exactly like optimizing a smart contract where yeah, you like kind of know the shape of your inputs and then you like can like manually validate stuff and can like manually validate, inputs and then do your write some more optimized code or something. Like because a compiler, it's a little bit more meta, right? You're like optimizing some unknown code um, for maybe some kind of unknown use case. And so you have to think like very um, defensively in terms of like what are all the possible things, or what is the entire input space of programs that could happen, and could any one of them break this optimization? Um,
Beautiful,
yeah,
beautiful. Can we keep on? Let's keep on with the AST
yeah.
question.
Yeah, so it turns out, this is kind of a fun optimization actually, which is for is if we're in a truthy area, which is like an if, um, so something like if you know x and then branch A, branch B. This is going because the EVM only has jump I. EVM only has jump I, no jump I. So this always ends up being like pond 0. Call this join. A join point is in compilers is where the branches join. Um, so we're gonna say we're only gonna do one branch. So here we've got so if we only have jump I, so we can only jump if the condition is 0, or like we can only jump one direction. So we have to like actually invert the conditions, and then if the condition is 0, we jump past the join, past the branch into the join point. Does that make sense?
Interesting.
So and then because jump I only actually operates on truthy values, it doesn't care if it's 0 or 1. It actually only cares if the input is 0. If we have something like if cond already has 0 in it, then we get something like and we're going to get some code like this. And then so this is really interesting because the IR quote unquote optimizer is actually inserting instructions, and in the assembly where there's a rule which replaces is 0 with nothing. Label jump I. And I can show you the there's a rule for that. So here in the assembly, so the entire code gen for Vyper is like 1,000 lines, and that includes the assembly optimizer, which doesn't do that much, but it does stuff like merging these is zeros. So it removes dead code, it removes useless jump deaths, stuff like that. So finally, if we go to this, and this is a lot of time I like to look at the assembly, which is basically the same as the runtime opcodes, but we have labels instead of these weird jump things. So we have so if we look at this, like we have like is 0 sim revert jump by, and that jumps the shared revert block. And then if we remove the optimizer, if we add back in the optimizer, then we skip the is 0 stuff. And same with here. So dupe2 is 0, this jumping past this branch. And here we have dupe2 XOR jump by, which is like, saves an instruction every single branch, which is not too bad. Um,
XOR consider if any of the values are true, right?
Yeah, and I don't want to get too hung up on this because it's just like one particular optimization.
Okay.
Um, but yeah, so that's kind of this is kind of like the life cycle of, and so the life cycle of a contract, or as it's compiled. And so, I mean, most of the time when I'm like writing part of the compiler or like adding something, I'm thinking about IR, and then like this stuff kind of just like kind of just think that it eventually gets optimized to assembly. So if we like look at I don't know how an external call gets implemented, um, we do all this stuff. We do like ABI encoding. We decide to use static or regular call. We have a check. External call is like a check call, so it checks if the result of the call is 0, and if it does, then it reverts. And then it checks the quarks. So this is how we implement all the optional arguments to any particular call. So like the value, the gas, and these are special Vyper things like skip the target contract. Anyways, all this stuff is like implemented in IR. So in general, yeah, and that's another reason to use IR, which is like it's just easier to write this stuff than to like have to write stack instructions and reason about stack instructions. Um,
Um, to interject really quickly, could you explain like Viper's whole trade-off with the stack? Because I was talking with I think it was like Z80, and he mentioned that Viper will store all variables in memory regardless, and then pop them onto the stack when they need to be used inside of an expression. But I know Solidity will generally keep everything on the stack, and so like, what does this trade-off look like? And I was just kind of curious why it was made. Like, is it solely stack too deep?
I think that it was probably done. I didn't decide that. I think Vitalik did that originally, or somebody must have. But um, I think it's mainly stack too deep. The trade-off is there's a couple interesting things. The trade-off is a little bit of code and gas size, code size and gas, because you have to load and store things from memory. Ideally, we would put more things on the stack, on the to-do list, I guess. And then you also get to avoid any kind of stack too deep stuff. So if we look at this example a little bit more, we can do this now. So 256 equals 0. Return something. And then we're going to see a bunch of M loads and then M store into the return buffer. So the main reason for that is, yeah, it's stacked too deep. And then there's also stack scheduling. So it turns out that scheduling stuff, so if you have like 3 variables on the stack or something, or 5 variables, A, B, C, D, E, and then you need to reorder them somehow so that like it's like A, C, D, I don't know, C, D, E, A, B, I don't know. Sometimes it's easier to do that. Well, you don't really have to think about it if they're already in memory. You just like M load them in the right order. But if they're already on the stack, then you need to do some like complicated stack scheduling thing, which is like kind of a big problem in compiling for the EVM in general that kind of want to work on, which is like the stack scheduling in the optimal way isn't really a solved problem. And right now, the methods for stack scheduling are a little bit um, are a little bit naive. Um,
Awesome, bro. Can we take a look at the Titanoboa?
Yeah, let's look at Titan a Boa for a little bit. I'm actually working on something fun right now. But let's look at the architecture of Titan a Boa.
Awesome.
So, um, Titan a Boa is a Vyper interpreter, and the way it works. The way it works is we basically, so Titan a Boa has two main modules, I guess. Environment, which is basically wraps PyEVM, and this like you can think of it as like the back end for Vyper, and then we have this Vyper contract abstraction, which you know models what is a Vyper contract. And a Vyper contract is basically it's got its source code and then it's got the compiled code, and then in order to use it, so the fun thing about Titanabo is you get all 100% hyper functionality, and the way you do it is like you don't implement a different interpreter, you just compile to EVM and then run the EVM interpreter locally, and then kind of figure out instrument what the EVM did. So there's like a bunch of stuff in here in the environment, which is like you just like look at tracer for instance, which like kind of traces what PyEVM did. So like when we want to get the trace of the opcode trace, we monkey patch PyEVM. So there's a lot of monkey patching actually, and that's actually something that is built as functionality into Titanable, which is like you can patch any opcode.
What you mean by patch?
So by patch, I mean we take the functionality that was there and change it. So we can like even
Nice.
like 0x, I think. Um, so if we wanted to, we could like add. Actually, one thing that is relevant to me today is like mcopy. So like if we had an mcopy implementation, I don't want to do that right now. Let's suppose. Sorry, a little too all over the place. But you wanted to know what I meant by patch. So this is our
This is the
implementation of SHA-3.
implementation.
Yeah. So this is.
That's really interesting. You also have like cheat codes or custom, implementations.
Am I still here?
Yeah, we can hear you.
Got a little disconnected for a second. Anyway, so this is because we actually want to find out what is in a contract. So contracts might use SHA-3. You can't generally reverse engineer what's in a contract in a human readable way without like knowing without being able to break SHA-3. So like if a contract stores something in a mapping, then the keys get SHA-3 and you can't like figure out where they came from. So in order to address that, we patch SHA-3. This is gonna be easier if I just like show you.
Oh, actually, really quick, this brings up something that I wanted to ask about. Um, how does Vyper handle nested mappings? Because I was talking with someone the other day, and like apparently Solidity, if you have a nested mapping, it'll hash the first key and then hash the second key. But I'm hoping that Vyper would just combine both keys and only hash once. Um, I'm sorry, I just like the SHA-3 hashing brought it up to me.
I think that we do two hashes, but we could look at that. So actually, this is a good example. So here we've got uh, right? Okay. We're looking for allowance. Yeah, we do two SHA-3s.
That makes sense.
So which we might be able to change, but I haven't thought about it very much. Oh, I forgot what was the symbol decimal supply. No. And so here we're already setting something in the balances map, so we get a SHA-3. And the reason it is important is because if we look at this, we actually see we can actually reverse engineer what the storage is. And we do this by tracing all the SHA-3s. So if we look at Vyper contract, like we look at everything in this in the contract storage, and then we look at our traced preimages, and then we can calculate this cool map, which looks like this. And then if we then t dot transfer recipient equals quote. This is very off the cuff. If we transfer to recipient, we see we get two more SHA-3 traces. And then if we look at this, see that, you know, the balance mapping has changed. So that's what opcode patching is. And using that, we can like kind of get fairly interpreter like, well, it is an interpreter, but we can get like fairly high level interpreter characteristics, even though we're using this low level interpreter.
Nice. Do you also have custom functions? Like for asserting tests and stuff?
Yeah, so so we hook into test. So anything, if you import BOA, things will just like kind of work. We can actually look at some of these things. So here's one fun thing is we can inject code into contract. So here's like some contract, and then we want to inject this code into it. And the way we're actually able to do this is a little bit fancy. So a contract object has this thing called inject function, and then it constructs this inject Vyper function. And the way that works is it will replace the bytecode that you're calling with the bytecode of the function at the call site. Call that instead. So with that, you don't need to insert your testing functions into your contract and kind of like dynamically inject internal or test or external test functions into your contract and then call that your testing. So here we're looking at this PyTest and hypothesis, and this just kind of all works the way you would expect. So you've got this contract fixture, and then every time you call test inject, it starts with, it gets this fresh state, and then goes back to the fresh state at the end of the test call. Does that make sense?
Yeah, and bro, I see you using Vim like this, I feel like trash, you know.
No,
Using VS Code and being all plug.
it's just habit, because I'm old. Um,
Every compiler dev
anyways,
I've met always uses Vim.
it's because we have to look at a lot of text files. Anyway, so do we still have this? No, we don't. So let me talk about how we would implement mcopy. And so I don't know why I didn't use patch opcode because I added patch opcode later. Basically, I think that's what we need. And then I'm just gonna. So I think the way we would test this, and we don't actually have a Vyper compiler which generates mcopy yet because it's still under consideration for Cancun. Um, it's just source. Source length. So we're computation dot stack dot. I'm really just making this up because I happen to know. And so let's see. EVM. We want write bytes. Bytes. Array. Right. Sorry, I'm just like trying to do a demonstration.
What we're looking at.
This is the Pi EVM implementation.
Nice. These bytes.
Is this Gacon's PyEVM wrapper REVM?
No, this is Pi EVM itself. The
Does
underlying object is
Titan then use
recognized.
PyEVM? Because I think ApeWorks uses the Const wrapper version, or
Works will is different. It uses it calls a node, so it interfaces over RPC with you know Anvil or Hardhat or whatever.
makes sense.
So I think we're just um, oh, I think this is how you would implement mcopy. So, but basically, I'm just trying to demonstrate how you would patch
Really nice.
an opcode in Titan Aboa. So the point is it's quite flexible, right? So you can like take
Can I
your EVM
can I have different
the way you
files
want,
for each one of the classes for the functions?
of course. Like
Awesome.
so normally you would do it in like a completely different file. Oh, right. So that's how like breakpoints are implemented. I forgot. So Vyper will actually emit this opcode A6 if you have a breakpoint, which is like some big opcode, and then it'll like start the BOA debugger, and then
And bro, are you involved in any products or companies? I mean, are you working with anything besides Viper?
work on Vyper.
Awesome.
So that's in principle how you would patch an opcode, and then right, so this architecture makes it pretty flexible. And then so what I've been working on recently is actually so far, well, up until a little while ago, a few days ago, was like simulation only. So you just like run stuff against PyVM. Um, but if you it turns out that if you plug a different environment in, you can get different behavior because the environment is like the backend. So implemented this thing called chain environment, which is basically going to make calls to an RPC. So now you can use Titan Aboa to like deploy code
Nice. You can create scripts and
or
everything.
like interact with a node. Yeah. So you
And
can right exactly. You can write a script and you can use it like basically just like any other framework. And what I was working on earlier is actually something that will let you. Oops, I'm gonna save this because this might be useful. Is actually something which um, overrides the signed transaction functionality. So normally in when Bo is interacting with an RPC, it'll take like a local account, so like a private key of in memory, and then sign transactions and deploy whatever you want. But this is something which you could do from a Jupyter notebook. So what it's going to do is you're writing a contract, and then you like call like contract.deploy, um, and then that issues a signed transaction request to the user, and then you can sign it from MetaMask, and then it'll deploy from your Jupyter notebook.
What is the pipelines you have today to deploy Viper and everything? Running the tests.
Like Vyper contracts in general.
No, like the compiler itself. Whenever you need to put out a new release, do you have this cycle that you go through? Any CD, any CI, or anything like that?
Yeah, so I mean, of course we have generally, continuous testing of Vyper. And then most of it, most of the release process is pretty automated now. We've got like workflow, which like whenever we have a release or somebody hits the release button, we upload it to pip to PyPy. Um, we also have a Docker hub, which is like always pulling any release tags and building them. We're also hosting work Docker images on GHCR, which is like GitHub's container repository.
Really
And then
nice.
lastly, we're also, as of recently, hosting stuff in this Viperlang dot slash Viper builds, um, which publishes builds for every single commit of Viper and all the releases. Um,
What was the most challenging thing you worked so on until now?
Most challenging thing. The most challenging thing is always going to be anything involving code gen in Viper. So
So creating
a few years ago,
contracts and everything.
no, definitely anything touching code gen, um, refactoring a bunch of the code gen modules. So Viper used to have like inlined ABI encoder, like copy pasted ABI encoding and decoding. So there was a bit of a mess because like some things that involved ABI like would work and some other things like wouldn't work. So like for a long time, like you couldn't emit events with like bytes in them because the ABI encoder only worked for like functions and stuff like that. Like
Well,
nested stuff didn't work. Yeah, so um, refactoring all of that, um, and the calling convention for Viper. So the calling convention when you called a function in Viper used to be pretty different. Um, it used to take all the memory variables, uh, push them onto the stack using mload, and then allocate, and then start the internal function, the callee function from like the zero area in memory. Basically, it didn't really have a call stack pointer, call frame pointer. And then after the callee returned, all of the all the memory values that had been backed up to the stack got restored to memory. Anyways, so now the calling convention is a lot simpler and also relies on the fact that in Viper recursion isn't allowed. So you can actually statically calculate what the call stack is going to look like, and you can have a bound on it. So instead of dynamically allocating call frames at runtime, there's no call frame pointer. All the call frames are just like somewhere in memory, and they don't have any overhead of like the size or anything because it's all statically known. And then it actually goes outside in. So you have like an external function like foo, and that calls bar and baz and cux or whatever. Then those are allocated from the outside in. So like if foo calls bar, calls baz, calls cux, then like all of those frames will be allocated in descending order.
nice.
And then the calling convention is pretty simple. You just like it's just a memory copy. You just copy stuff into the argument buffer for the internal function, and then it gets written into the output buffer.
What things are coming for the language, bro? What things are coming for Boa? You have anything planned? Where's the roadmap?
Yeah, so the biggest thing on the roadmap is modules. So Vyper, which I've been talking about for a long time, but keep seeming to well, there's a lot of stuff that needed to happen. So um, we recently got a bunch of feedback from a couple auditing firms, and so fixed a bunch of bugs. Um, the biggest thing is Vyper was originally conceived of as like a single contract, as a single file language, which sounds, kind of fun in theory, but in practice it's not because like in the real world people want to be able to reuse code without copy and pasting. Um, but unfortunately the compiler was architected that way, so a bunch of refactoring work has been being done in order to make it possible. Anyway, so the next big thing is to have a module system for Viper so that you can import functions. And I think it's actually going to be quite cool the way it works. So there won't be inheritance, but you'll still be able to import modules that operate on storage. And the kind of key point is like how storage gets encapsulated. And there's some ideas about that. So that's the big thing on the roadmap. Another thing is the backend. So I think Control C plus Control V. Sorry, maybe I should just call you copy paste. But copy pasta asked about Venom IR, and Venom IR is this planned new IR, or maybe implement done as a redesign of the current IR. But anyways, um, the idea is it's going to be designed in a way that makes it much easier to target stack machines, which most smart contract VMs are, and target stack machines in a way which keeps code size small, because that isn't really a constraint which affects other existing stack machines like, .NET or JVM or whatever. People just kind of commit whatever stack machines, not in a super careful way, and then because that stuff is all JITted, so they can rely on the optimizer at runtime to do a really good job bringing it to machine code. But in the EVM, we don't have that luxury because everything, all gas costs are like determined like um, defensively, and, and we also have like these code size limits, so you can't like generate really inefficient or really large contracts. You have to like try to keep contracts as small as possible. Um, so anyway, and also it comes in handy if we want to have Viper target other stack machines, more easily, not only EVM.
Just curious, does Vyper or on the back end, are there changes that would ever allow using like Huff linked libraries from within inside of Vyper code so that you could just embed Huff into your Vyper contracts?
Um, it's an interesting question. Um, so first of all, I don't think that we would. Uh, it's a complicated question because first of all, we don't really want to allow low-level code in Viper contracts because it violates some safety invariants. So like once you give people access to low-level code, you can kind of do anything. You can start like overwriting memory. You can start touching any parts of storage. So there's usually two reasons why people request that. One is um, the compiler isn't generating good enough code. It's like not optimized enough, which is like, okay, then we want to fix the optimizer. The other reason is people want to access some feature which is not available, some feature in the EVM which is not currently available in Vyper. Like, I don't know, some new create instruction or something. And, that's kind of more compelling. I mean, we should also like give people the features they want, but maybe at some point it's unavoidable. So we could, expose. In fact, I have an open pull request for a system built in, which allows you to like inject arbitrary bytecode into a Vyper contract. I'm not sure we would necessarily use Huff. Like, I think our assembler is pretty good. Um, or like being able to inject IR into the Vyper contract. But it's more a question of if we want to allow that, because it also kind of breaks things for the optimizer um, if you can't assume as many things about um, like how IR is being generated. But I think that the big thing is like just getting the optimizer better and re-architecting, redesigning the IR in the way that's best for that is like something that I think is really important going forward.
So it makes sense. I mean, I definitely understand like the black. You can't just inject a black box and then expect it to be more efficient because then the optimizer can't really do anything with it because it is just arbitrary bytecode.
Really nice, really nice. Anything else you want to show us, Biggie?
Uh, there was if you have some more questions, I hope I didn't like trail off or like get
It was really good.
start on a different
A lot
tangent
of
when I was
alpha,
like answering a question.
a lot of alpha. So you guys have questions? I guess one question for me from me would be I want to start, diving into the EVM itself, understanding the compiler, understanding these low level operations. How do I start, bro? Should I go and learn the x86? Should I go and, play with some EVM CTF or just read a book? What is the best way?
Um, I would maybe I'm biased because this is also I guess how I learned about the EVM is by working on Vyper. Um, I would recommend actually just like looking at the IR and assembly outputs for any Vyper contract and also like read the compiler. I think it's fairly approachable at this point. Um, and
Interesting.
kind of just see what it does. And there's a lot of implementation details which are interesting. I think fairly well commented. And you can also pop into the Vyper Discord at any time and kind of just ask any questions about how things are implemented or why something was done this way or other.
Really nice. Really nice. And yeah, definitely something that I want to do. And yeah, let's start collaborating more. Anything else? Any questions, guys? That's not. I'm gonna. Charlie, Charlie, you have anything to say? Any closing thoughts? You want to invite people to check out Viper? So this will be on YouTube. So maybe leave it a message.
Uh, in a message, I do that. Chat.
Come and check out Viper, right?
Yeah. Vyper, check out Titan Boa.
Amazing, buddy. Amazing. Great work. Thank you so much for doing that for the industry. Not every day, and also here, very humble guy. Thank you so much for your time today, and this is it, everybody. Okay. See you
Thanks for
guys.
having me.
No
Thanks,
problem.
guys.
No problem.